Hello everyone, myself Anamitra and I work in Samsung Research Institute, Bangalore. I will walk us through our work which is LiteAR, a framework to estimate lighting for mixed reality sessions for enhanced realism. Realism in augmented reality is challenging. Lighting, occlusion, they play major role in bringing realism. There are two light sources in an environment. So apart from direct light source, the surrounding environment can act as an indirect light source. Lighting has two components, diffuse lighting and specular lighting. We address the problem of accurately estimating diffuse lighting for an environment. Here in the image B, so this bunny is the virtual object which is placed near the pool. So we can see that some kind of bluish effect is visible on the virtual object as it is placed near the pool. So that is the kind of estimation which we are trying to do in our work. IBL, image based lighting, is a very well known technique in computer graphics to do the lighting. So what happens in IBL is usually stored in the format of a cube map. So given a panoramic scene, there are tools which are publicly available which can convert that particular panoramic scene to the cube map, and given the cube map we can do the lighting in computer graphics. If we want to implement the lighting in augmented reality, we need the panoramic scene which the camera is seeing, but the problem here is camera only sees 6% of the panoramic scene. So our goal is to predict diffuse lighting for the environment from a limited FOV photograph in mobile in real time. So there are related works in this domain. Some of them involve light probe, some of them do not involve light probe. So light probe is basically a mirrored sphere which is placed inside the scene. So all lighting information will be captured onto that sphere, and with the help of that sphere we can do the lighting. Light probe based techniques are very efficient, but we cannot have a light probe in every scene. So if we are implementing augmented reality in a mobile phone and the works which do not involve light probe, they do not take into the account the impact of the local environment of the object. So we'll explain these things in more details in upcoming slides. In essence, our work can be summarized in three main points. So first, we have a lightweight framework to predict the diffuse lighting. How you do that? We have a lightweight neural network. Then we estimate the irradiance map as a set of spherical harmonics or SH based coefficients. And the second thing is enhancement based on object's local environment. So we have point cloud representation of the depth map. With the help of the depth map, we take into account the object's local environment. And the third thing is we made use of IMU sensor which is sitting inside the phone. Basically this sensor gives us the rotation angle for the phone. So let's say in the scene let's say the scene has not changed much. Let's say my phone has rotated by some angle from the initial position. In that case, what happens, we get the angle from the IMU sensor and we update some of the coefficients to do the lighting. So basically that helps us to reduce invoking of neural network every time. So now I am going to introduce to spherical harmonics. SHs are basically functions which are defined on surface of a sphere. So in this image I have shown 4 bands of spherical harmonics. So first band, second band, third band. So blue part is where the function is positive and the yellow part is where the function is negative. So we can think of like some basis function is there which becomes negative in the yellowish part and which becomes positive in the bluish part. So in our work we have used 3 bands, first, second and third. So that basically gives us 9 coefficients. So now we calculate irradiance for each of the points to do the rendering, and to do the irradiance we have 3 parameters. First one is the constant, the second one is the one which we are trying to predict from this equation, and third one is the SH. And for the second one we need the light distribution function. So if we have a complete panoramic scene available with us, we will have this distribution function also. But since camera only sees 6% of the image, that is what we are trying to predict. So once you predict this L subscript LM, we plug this into this equation, then we get the irradiance, and with the help of irradiance we do the rendering. So we take 9 coefficients for each of the RGB channels, so that basically gives us 27 coefficients. This is our overall pipeline. So first we have the input camera image from the camera, then we give that image to the neural network, which gives us 27 coefficients. Based on that we do the lighting. At the same time we have a depth image point cloud data for that particular image. With the help of that we update some of the harmonics to get the local impact of the local environment. Then we get the rotation angle from the IMU sensor, and we update some of the harmonics based on that rotation angle, and then again we do the relighting to take into account the rotation of the mobile phone without invoking the neural network. Sorry. We have used publicly available Matterport 3D dataset. It is having panoramas of indoor scenes and rear camera images. So in this example, this is the panorama image which is being given to this command line tool, which is publicly available in filament renderer, and which gives us the spherical harmonics, and we generate 6 viewpoints which are separated by 60 degrees. So one of those viewpoints has been shown here in red rectangular box. So basically one rows of the dataset contains 6 viewpoints which correspond to one panoramic scene, and then 27 coefficients from the publicly available tool. So now coming to the network, first to resize the image to 420 cross 320 pixels. So our model is basically blocks of convolution layer followed by the max pooling layer, and they are having ReLU as activator. We have tan H at the last layer, which gives the predicted output in -1 to +1 range. Then we have used two loss functions. So first one is the mean square error on predicted SH coefficient, and the second one is the pixel to pixel loss. So pixel to pixel loss among the sphere rendered by the ground truth SH and by predicted SH. Then we have used Adam optimizer for training. So in this slide I am going to explain spatially varying environment. What happens is this virtual object, which is a sphere, it is placed just below this table. So at the left side of the sphere there is this dark wall is there. So because of that, some kind of black effect should be there at the left side of the sphere. So that is what happening in the right side. So after we take into the spatially varying environment, we can see that some kind of black effect should be there. So some kind of black effect is visible at the left side of the sphere because of this dark surface. So how you do that? So we can imagine a sphere surrounding this particular virtual object. So every point on this sphere will act as a light source. So basically the data which we get from point cloud, we arrange that in KD tree for efficient querying. So we update first to bands of spherical harmonics, and the formulas are inspired from Monte Carlo integration, and we update other harmonics based on the first two harmonics, which is by taking help from these two equations. So after we take into account the spatially varying environment, the sphere looks like the image which is in the right side. So now coming to the rotation. So as we told earlier, we get rotation angle through IMU sensor. So basically the first band can be treated as a scalar, the second band can be treated as a vector, and for the L2 band, which is having 5 components, so we made use of this theorem where rotation followed by projection is commutative. So now coming to the result part. So when we do the lighting at the global level, so when we place the virtual objects onto the pool, we can see that some kind of bluish effect is visible on the objects. Similarly, when they are placed in an environment where some red floor is there, some kind of reddish effect is visible on the objects. The same thing can be said about the third row and for the fourth row also. Now coming to the rotation. So the first row, this is the first image, then we rotate the camera by 60 degree, then we rotate it by 120 degree, then we rotate it by 180 degree. So in the second image, we give each of these images to the neural network, which gives us the spherical harmonics, and with those spherical harmonics we do the lighting. And in the third image, so we have the spherical harmonics for this image, then given the formulas which we described in the previous slides, we update some of the coefficients and we do the lighting. And to measure the difference between two images, we have used SSIM index, which is a qualitative index based on the perceptual difference between two similar images, 0 being the lowest, 1 being the highest. We can see that second and third row, they are having very high SSIM index. So here we can see that this bunny, it is being rendered on top of a pinkish bed. So in the image A, this is illumination at global level, and image B we take into account spatially our lighting. So we can see that image B, it looks more realistic compared to the image A. Now if we compare our work with the already existing state of the art works, so we focus onto one of the parameters, which is multiply accumulates, which is a very important parameter for the neural networks. Also one more thing, SH rotation, which we explained in earlier slides, that only requires around 120 multiplications. So you can see that with respect to MSEs, our network is much more lighter than the existing priors like DeepLight or Gartner or PointAir. And when we compare the results, we can see that compared to other state of the art works like DeepLight, Gartner, our work also produces very similar results if we compare our results with those works. So in terms of L2 loss also, we can see that our network is comparable to other networks also. So here one thing which we want to focus on is that although our network is very lighter than the already existing state of the art models, but in terms of L2 loss, our network is very much comparable to other state of the art models. So in concluding remarks, we can say that we have a pipeline which operates much faster than the state of the art methods. Also, we believe accuracy could be improved with a more varied dataset. So, and we believe dataset could be naturally enriched by introducing pictures which are taken from different mobile phones in different environments. Also, one more thing, in point cloud setup, the radius of the sphere, that is experimental now. So if we come up with some function which can give us the radius of that particular sphere dynamically, so that will bring more realism to the final outcome. So these are the references for our which we have referred to do our work. I would like to thank you for your attention and for your time.